Hi everyone, just wanted to make a brief video here to go over the procedure for simulating and extracting some key MOSFET parameters. I've set up here a simple test bench with an NMOS transistor, gate length and width shown here. It's based on 45 nanometer uh, open source MOSFET models. And you'll see that I've applied a drain source voltage of only 10 millivolts at first. And we're going to do a DC sweep here where we sweep the gate voltage. So don't worry about the value shown here. And as we increase the gate source voltage above the threshold voltage, it'll immediately go into triode because the drain source voltage is so small. So you'll see also I've got a probe connected to the drain to monitor the drain current. And this probe here is monitoring the differential of the drain current. So essentially that's going to result in a plot of GM, small signal transconductance of the MOSFET, as we perform this VGS sweep. So let's go ahead and run that simulation. We're doing a DC sweep from 0 to, let's go up to 800 millivolts. This technology is probably fine. And go ahead and run it. Okay, so here's the plot. The bottom plot is the drain current versus the gate source voltage. So a couple things you'll see here. The transistor's turning on somewhere at a gate source voltage of about between 300 and 400 millivolts. And we see it goes into triode, so the drain current increases linearly with further increases in gate source voltage beyond that. And if we wanted to extrapolate the threshold voltage here based on this IV characteristic, what we would want to do is take the linear part of this curve and then extrapolate it back to the x-axis. Now the curve is, not linear for very long. It's curved everywhere. One good approach to pick at which part of this curve should we assume is the linear part. One good approach is to just look at the peak of the transconductance plot up here, right? So at this point here, we can assume that's about 550 millivolts gate source voltage. We can take the slope of the bottom curve, extrapolate it back down to the x-axis here, and we would find the threshold voltage probably just over 350 millivolts, just eyeballing it here. Okay, so that's what we see for the IV characteristic when we've got a small VDS applied. Now let's go ahead and increase VDS. Let's go up to 800 millivolts and rerun the simulation, see what happens here. Okay, so now the drain current looks quite different. Again, we see the transistor turning on generally in the same general area, and it looks a little bit more quadratic in this region. This is the classic MOSFET square law. But then again, it looks like it's becoming linear. So this is not unexpected. If we look at the plot of GM versus a gate source voltage up here, we see that it's off, and then we've got a portion of the curve that's linear. So when transconductance increases linearly with gate source voltage, that means the drain current is increasing quadratically. That's our classic square law. So in this case, the range of validity for the square law is kind of in the range of, 2 to 300 millivolts, maybe more like 300 millivolts, up to maybe 450 millivolts. So again, a very narrow range of gate source voltages over which we see the square law. If we take the linear part of this transconductance curve and extrapolate it back down to the x-axis, it would intersect the x-axis at a much lower voltage, around 220 millivolts and before. So that's the procedure we would use to extract the threshold voltage from this saturation mode of operation for the MOSFET. And not surprisingly, for this very small gate length, 45 nanometers, we see a threshold voltage much lower than what we saw in triode. It's lower by probably about 150 millivolts. And that is the drain-induced barrier lowering that results from the much larger drain source voltage we've applied here, 800 millivolts instead of just 10 millivolts. So again, you see the transconductance curve is the right plot to use here for finding the threshold voltage, because this plot here, it's too, it's not clear just by eyeballing this plot where the square law is valid, but it's much, much more evident by looking at a plot of transconductance versus VGS. Something else interesting to look at here would be to add a plot of GM over ID. So let's go ahead and do that. If we add that to the axis over here, here's what we see. That's the blue plot shown on the top axis. And we see as the transistor enters subthreshold, it's approaching a maximum of about 20 over here. Now, you may recall that that plateau in the GM over ID plot should correspond to a value of 1 over N times the thermal voltage. So this simulation is being done at around room temperature, so the thermal voltage is about 25 millivolts, and it turns out that with a value of 20 here, that predicts a rather large value for the transistor parameter N, the subthreshold slope parameter. It's around 1.8, 1.9. That's the value predicted here. So that's quite large. Sorry, it's a little bit hard to believe. But in any case, that's part of the reason we do these simulations, to validate the models. We've got to validate our simulation procedures. We can also try and estimate the subthreshold slope parameter N by adjusting this bottom plot here to be on a semi-log scale. So let's go ahead and do that. And when we do so, we see this part of the curve here is a straight line on a semi-log plot. That's what we would expect in subthreshold, where we expect an exponential IV relationship. And if we look at the slope of this curve on a semi-log scale, we know that it can also be used to extract the subthreshold slope parameter N according to this relationship here. So specifically, we expect ID to increase by this factor for a delta V increase in VGS while we're in that part of the curve, while we're in the subthreshold portion of the curve. So again, just eyeballing it here, we see that the drain current increases by about 1 order of magnitude, factor of 10, with a VGS increase of about 100 millivolts. And if we plug those numbers into a calculator, we again, assuming room temperature, we again get a subthreshold slope parameter N somewhere around 1.75, 1.8, a little bit lower than what's predicted by this value up here. So the lower transconductance here than we would expect based on N extracted from this plot may be due to some resistance, some series source resistance due to a lightly doped source region or something like that that's sort of denigrating the small signal transconductance of the MOSFET. So that would show up in this plot here, might not be as evident in this plot here. So I would tend to believe the value of N extracted from this plot a little more. So that's basically it. And last thing you can see the old plot for ID versus VGS here and the new one here. And you see that as we changed the drain source voltage, we went from 10 millivolts to 800 millivolts. We see the Dibble effect clearly here. We see the break point from subthreshold operation to weak inversion and strong inversion definitely shifted to the left. Again, another indication that the threshold voltage is decreased by the large drain source voltage. And that's it for now. Thanks.